Hi, this is my lab 2 projectile motion. So, an introduction. The goal of this lab was to analyze the two-dimensional motion of a projectile. I threw a stress ball into the trash can and recorded its motion from the side using a stationary camera. The video was analyzed in Tracker to extract position versus time data. So, the physics principles slash models used here was Newton's second law, the momentum principle. For model one, it was gravity only. We used the physics principle of force, which is mass times acceleration, where the vertical acceleration was due to gravity. The Model 2 was gravity plus drag, included air resistance using the drag force, which is expressed as the equations as seen right here. So brief preview of my main results was so the experimental trajectory was plotted against both models. Neither model perfectly matched the experimental data. The experimental path stayed above both models until the final moments. This suggests that the drag coefficient was the factor affecting the motion and needed refinement. The main physics ideas here was drag force, Newton's second law, gravitational force, position updated equation, and the velocity updated equation. Here are my explanations below. The main physics ideas with visualization. So here is my graph that shows the y position versus time for the thrown stress ball. The blue line is experimental data collected from Tracker. The orange line represents the model with gravity only. The green line represents the model with gravity and drag. The reasoning behind the model assumptions and physics principles. So I used Newton's second law to build computational models for the net force, and that was used to update the velocity position at each time step. The gravity-only model helped isolate the effect of gravity on the object's vertical motion, while the drag model allowed me to incorporate air resistance, which became noticeable in real-life projectile motion. The system and surroundings. So the system was the stress ball in the air after being thrown, and the surroundings were was gravity, air, trash can, and the floor. The trash can and floor was part of the environment, but not part of exerting the force on the system. The initial conditions for the experiment and combinational model. So we have here is the initial position of the stress ball. I set it to 0 for X, and then Y was 1.524 meters per second, and this was found through Tracker. The initial time was also 0 seconds. From the Tracker data, I calculated the initial velocity, and this was based on the change in position over time in the first few frames. So the initial velocity was approximately for X negative 2.58 meters per second and for Y negative 0.312 meters per second. The values were entered into both the gravity only and drag included models to keep conditions consistent across all simulations. The drag settings. So the no drag model had the B equal to 0, which is the drag coefficient, and the drag model had B equal to 0.05. Here is my coding. So for on the left, we see for gravity only model with no drag, and that's because B is equal to 0. And for the right, we have for gravity plus drag model, which I had set to 0.05. The ball mass is 0.29. And here are my ball position vector and the ball velocity vector. They were set the same. Here's my experimental setup and results. So I set my setup and tracked path and tracker for my experiment is shown right here, where I'm throwing the ball into the trash can, my stress ball. And I use this data to compare two models, one with gravity only and one with gravity plus drag. The images next to the tracker setup, right here, show both models running with the same initial conditions. The similarities and differences between the data and model predictions. So the experimental data similarly showed a parabolic trajectory, but did not perfectly match either model. The gravity-only model predicted a sharper curve downward, underestimating the vertical position. The gravity plus drag model followed the trend more closely, but still showed deviations. These differences highlight the role of air resistance, which was modeled as a force proportional to the velocity squared. Possible sources of errors include inaccuracies in drag coefficient, which is B, experimental human error on my part, which included tracking inaccuracies, calibration issues, and the frame rate miscalculations. And then finally, simplified assumptions in the models with using only vertical drag. And then for answering the what if the object was thrown straight up with the same initial speed, I say that the object would take longer to reach the ground than it did in the original experiment. In the original experiment, the object was thrown in a parabolic arc and reached the ground relatively quickly. If instead it was thrown straight upwards with the same initial speed, it would first rise until its velocity became zero, then reverse directions and fall back down. So using a kinematic equation as seen here, it justifies the overall time being longer because the object must go up and then down rather than just forward and down. And then what does it mean? So do my models predict terminal velocity? For my gravity only, no. And for my gravity plus drag model, yes. Because terminal velocity was not observed, we can design a new experiment where the object is dropped from a greater height, or we can use a lighter object, example being a crumpled paper. Thank you.